All right, so in this lecture, I want to expand on what we learned about waves from the last lecture and talk about how we experience some of the wave phenomena from that we started to build the foundation for before. So first off, last time we only talked about transverse waves, and I mentioned that light was a transverse wave, water is a transverse wave, some earthquake waves are transverse waves. And but some earthquake waves are also something called longitudinal waves, and so that's what we're going to talk about here. And we'll start with sound. Sound technically isn't a transverse wave; it's actually a longitudinal wave. We could like to talk about it as being a pressure wave, but we also call it a longitudinal wave or a compression wave. Now, what's different about a longitudinal wave is that its amplitude is going to point left and right while the wave moves parallel to that direction. Whereas in a transverse wave, the amplitude was up and down, and the wave moved left and right. So I'll show you what I mean with a drawing, and I think this is probably the best way to understand it. But you can see here that a loudspeaker or just a speaker in general produces sound this way because it has a cone inside the speaker that moves left and right. And what it does is it compresses air, right, by pushing against the air. And then when it moves backwards, it creates a low pressure area. So we refer to this low pressure area as a rarefaction, and this high pressure area as a compression. Now, like I was trying to say before, the amplitude for these longitudinal waves or these pressure waves, the amplitude is left and right while the wave moves right. And so it's parallel to the direction the wave moves. The amplitude is parallel to the direction the wave moves, which is different from transverse, right? If you remember back to transverse, I can show you a transverse wave looked like a sinusoidal wave, right? And our equilibrium was right down the middle. And here our amplitude was up and down while our wave moved, say, to the right with some velocity. So this velocity is at 90 degrees to this amplitude, whereas this is parallel, this amplitude is parallel to this velocity. And this will continue, this compression will continue to move down the wave. Now you might say, well, okay, well then what is an amplitude for this wave? Here it was the distance from a crest or a trough to the equilibrium, and here it's going to be the length of a compression. And a wavelength then is the distance from the center of a compression to the center of the next compression, or you could say the front of a compression to the front of a compression. And even though we know sound is a pressure wave and is longitudinal, let's get a definition for what I was saying about longitudinal waves having amplitudes that oscillate parallel to the direction the wave travels. So if you want to write that down, you can add that right there. All right. So even though we know sound is a longitudinal wave, we sometimes like to talk about it as a transverse wave, and I'm going to show you what I mean by that in a second. So I'll let you finish writing that down. And when I drew this picture, I kind of just drew like 5 lines. Then I went 1, 2, 3, 4, and on the start of the 5th line, I drew another compression, then 1, 2, 3, 4, then another compression. You get the idea. All right. It's really a model for how it looks. So, but I try and draw the compressions and the rarefactions about even. Okay. So before we talk about pitch, or actually, yeah, I'll just show you what I mean here. So before I talk about pitch, this is what I was trying to say about how even though a longitudinal wave looks like this, right? We like to draw it like this. Sometimes other books will draw this as dots, and they will have less dots right here, and then more dots right here, meaning all the air particles are condensed and all the air particles are spread out, right? So the dots are representing the particles. But here's kind of another way to think of it, right? As a sinusoidal wave or a transverse wave, even though it's technically a longitudinal wave. And when you think of it this way, what you do is you draw pressure on the y-axis, distance on the x-axis, and then right here have atmospheric pressure right in the middle. And what this says is when a sound is made where there is a rarefaction, there is going to be a trough. So low pressure, right? Because the pressure's on the y-axis, so this would be low pressure. And where there is a compression, there is high pressure. And rarefaction, low pressure, compression, high pressure. And so you can see how sound is a pressure wave. And this shows the sound oscillating about P atmospheric. So that's about it. So another way to look at it. And we'll consider these compressions to be wave fronts. And I'm going to talk about that in a second. But I want to go back and talk about pitch first before I move on to talking about wave fronts. Because even though sound moves like this, we like to model sound as a sphere coming out from a source, unless it's being, projected in a certain direction, like a speaker will sometimes do. Sound just moves out in a sphere in 3 dimensions. All right, so let's go ahead and talk about pitch for a second here. And I think I mentioned this before, but I want to relate it to human hearing and the hearing of different animals. So here what we have is pitch being how we perceive the frequency of a sound. And so if something has a low pitch, like a bass note, it would have a low frequency. And for humans, our ears hear about to a minimum of 20 hertz approximately. This is the threshold of hearing, I guess you could say. Well, I don't know if you'd say that because that's related to energy, but you would say this is the lowest frequency. Frequencies under 20 hertz would be inaudible to human ears. We wouldn't be able to hear them. Higher frequencies, up to 20,000 hertz for human ears. Now, I know because I have a tone generator, and I just that as you get older and based on how well you take care of your ears or your hearing, you'll start to lose your hearing and you'll start to not perceive sounds near 20,000 hertz. So you have to be careful when you go to concerts and when you're listening to loud music. You want to make sure you protect your hearing. You can think about when if you do any construction work or anything with loud noises like hammers or anything like that, can damage your hearing. So anyways, so we have to protect our ears. But human ears hear up to about 20,000 hertz. So once again, this isn't volume. This is the pitch, a high pitch or a low pitch. And if we're older or our hearing is not as good from different experiences and is damaged, our range of frequencies will obviously be less than 20,000 and greater than 20 hertz. But I think you lose your hearing usually on the high end first. Okay, so let's look at this table on 481, and I'm going to show you that. Let's see. Just give me 1 second here to find it. All right. And I hope you can see that decently. What this shows is the range of hearing for different animals. And you can see humans, owls and elephants don't hear quite as well as humans. I guess elephants on the lower end of frequency. But dogs, the hearing of the frequencies that dogs can hear, you can think of like a dog whistle, can hear well above 20,000 hertz. And we like to call anything above 20,000 hertz as ultrasound or ultrasonic, and because it's above the frequency that humans hear. Mice, it looks like 1,000 to 90,000, which is pretty incredible. Bats, I guess no surprise since they use echolocation, and that while their eyesight's not very good, their hearing is obviously very good, and they hear 2,000 to 100,000, and porpoises 75 to 150,000. All right, so I thought that was kind of neat. Let's go ahead and talk about ultrasound a little bit. So let's define it first. Ultrasound is sound waves with frequencies above human hearing, above 20,000 hertz. So go ahead and write that down. And we also know that ultrasound has some medical applications, and one is to create images, right? Why ultrasound works so well is with these high frequencies, you have really short wavelengths. And so what ultrasound can be used for in the medical industry is to create real detailed images. So that is one application of ultrasound. Another one would be to heat up tissue. And so if you ever, say, have a damaged, I don't know, you can think maybe any kind of inflamed tissue. I was thinking where maybe like something like tennis elbow, something like that, that when that gets inflamed, you can use ultrasound on the area and use it to improve blood flow to the area by heating up the tissue. So I know that gets used in physical therapy a decent amount. All right. So let's talk about sound as 3D waves. And so I mentioned this a second ago. So sound moves out in spheres. Try and straighten this out here. Sound moves out in spheres from a source. And so I'll let you go ahead and write this down. Moves in 3D. So out from a source in a sphere. And we like to talk about the wave fronts as being where those high pressure crests are. So where as that sound moves out, that wave front is our high pressure crest, right, that we were talking about a second ago. So you can see here how there is between each crest or each wave front, since each circle, which is technically a sphere because I can't draw in 3 dimensions, is one wavelength apart because it's crest to crest to crest. And these represent the crests of the high pressure waves. So these represent the compressions, compression, 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 and the rarefactions would be in between that as it spreads out from a source. And I also drew the sinusoidal wave that you could kind of see. So you could see where the peak is, that's a compression, right? And then a peak right here. So I kind of added that to the sketch too. Now, some of these sketches on these notes are going to be tough, but I think you can make some of them. And obviously if it gets too difficult, then you can not do it, but try and write down as much as you can here. All right. So we haven't talked a lot about volume yet, and I wanted to mention that, but before we talk about volume, I want to talk about something called intensity, right? And because sound carries energy, and we know that if we've heard a loud noise near our ears, it can damage our hearing. So it's, even though sound isn't necessarily matter traveling through the air, it is energy, and it can cause the air particles near our ear to have enough energy to damage our hearing, right? So it is significant, and it is something we have to be careful of. So if sound moves out in spheres, just a reminder here, the area of a sphere is 4 pi r squared. I think the volume of a sphere is 4/3 pi r cubed, but anyways, area of a sphere, 4 pi r squared. Why is that important? Because in our intensity formula, which is just generically written as intensity equals pressure over area, I'm using a little a here because area, I don't want to confuse it with amplitude. I'll save capital A for amplitude. I know that intensity is capital I, which looks like current, and moment of inertia, I guess, as well. And but anyways, we have to ignore that for now and consider the context, right? So we use capital I now for intensity. Intensity equals the power of the source divided by the area of a sphere. Now, does also the area of your ear affect how you perceive the sound? Sure. So we can get a little more complicated than this as well, but we're not going to right now. We're just going to talk about the sound that is radiating out from the source in the form of a sphere, and that area of the sound or the wave front, that sphere being a wave front that hits you. So when your ear perceives that wave front, that sphere, this is the intensity that sound carries. Units here, power's units are watts, right? Because power is energy divided by time. Joules per second is a watt. Watts divided by meters squared, and meters squared, of course, for area. All right. Okay, volume. Volume is not intensity. And so you notice we've kind of skirted around this idea of volume, right? We haven't really talked about it, which is kind of crazy. We talk about sound, not to talk about volume. Because when we experience sound, we definitely always consider the volume. Here's what I mean by volume is not intensity. If one guitar is played, you would have a certain volume from that guitar. But if you played two guitars, it wouldn't sound twice as loud. And that right there is kind of difficult maybe to think about, but it's true, right? So what would be twice as loud then is a good question. And it's approximately, not exactly, but approximately 10 guitars played in unison, right, together would be about twice as loud. So what that means is increasing intensity by a factor of 10 increases perceived loudness by approximately 2. All right, so that gives you an idea. Okay, so why intensity isn't the same as volume, right? So what is volume then? Well, first of all, we like to refer to volume as something called sound intensity level, and represented by the Greek letter beta. This is lowercase beta. Anyways, volume is a ratio of the two intensities. It is the intensity of the sound compared to the threshold of hearing, which you can just perceive a sound at with its volume being as low as possible. So, and it has units here of decibels. So we're going to talk about sound intensity level as being our what volume is. So the ratio of intensities is unitless. We actually add on decibels, these units called decibels, by multiplying that ratio, which is usually a decimal, right? Because I think it's two ratios, and the smaller number is on bottom there. But anyways, I think when you take the log of it, it works out. But all right, coming back to this. So when we know that we are talking about sound intensity level, so decibels, it's unitless because you're dividing your watts per meter squared by watts per meter squared when you make a ratio. So anyways, we tack on this unit decibels, which you've probably heard of before when you talk about volume. So here's our formula for sound intensity level, which is beta, right? So this is what we are considering volume to be. Now this is kind of a complicated formula, right? But what it shows here, right, is that we take the log of our intensity ratio and then multiply by 10 decibels. And I naught, or I sub 0, is the threshold of hearing, is 1 times 10 to the negative 12 watts per meter squared. Intensity is whatever the intensity of the sound is. And so we take the intensity of the sound divided by the threshold of hearing, which is very small, right? And so we're going to end up with a number here, take the log of it, and then multiply by 10. So actually we're getting numbers of about 1 through 12 by taking the log of this, and then we're multiplying by 10 to get numbers around from 0 to, say, 120, 130. So it's not a decimal that's coming out of it. It's about 1 point, a number between 0 and 12, 0 and 13. The table for this, before we move on, I just want to show you that really quick. And the table for it looks like, looks like this. So what you can see there is the threshold of hearing is right here. And remember, when something is 10 times as intense, right? So this is multiplied by 10, it's twice as loud. So a person breathing 3 meters away, twice as loud of that would be a person whispering at 1 meter, right? And that would be 20 decibels. And then twice as loud as a person whispering 1 meter away would be a classroom during a test with no talking. Twice as loud as that would be residential street with no traffic. All right, so you kind of get the idea here. And it goes all the way up to 130 decibels, which is about the threshold of pain. So this would be where whatever sounds you're hearing is causing you physical pain. So that would obviously not be good. And that is where the intensity of your source would be well above 1 and at 10. So notice usually for a lot of these sounds, the intensity is very small, right? Because these are all times 10 to the negative. All right. I'm trying to think if there's anything else I want to add there. And I guess one thing to notice is if you ever mess around with like a receiver or stereo equipment, sometimes this decibel level starts with 0 at the threshold of hearing. I used to have a receiver where a receiver is what you plug your DVD player into, your Nintendo, your TV, everything goes into it, and then it also works as a radio. But anyways, my receiver, I think I generally listen to it at about, I think it was negative 19 or so. I guess it was decibels. I think it was. I can't remember off the top of my head, but yeah, I'm pretty sure that was what it was. And it worked off of a different decibel scale. So this decibel scale has 0 at its threshold of hearing. My receiver, when I was at negative 19, I could turn it down to negative 40 and it would get quieter. And if I turned it up to close to, like, say, like negative 1 or 2, close to 0, it was really loud. And so 0 on my receiver's decibel scale was where the sound would distort. And so they use that one in the radio industry, that decibel scale, where 0 represents where the sound or the intensity level where sound distorts. And so that way radio stations all are on the same decibel scale, and everyone knows that 0 is where your sound will start to distort. So here is obviously a different scale. So they use a different scale in entertainment than they would use right here. So that's what I wanted to say. Okay. Anyways, let's come back to the next page here. And so if we relate volume back to our picture of a wave, we can think about it this way. Volume shows up in our wave diagrams as intensity, and intensity is proportional to amplitude squared. So when you have a wave that, say, has twice the amplitude, so let's say you're at the beach or something and you see a wave, and then a larger wave comes and it's twice as tall. Well, does that wave have twice as much energy? And the answer is no, because intensity is proportional to amplitude squared. And we're thinking of intensity like volume, but if it's a water wave, then obviously you're thinking about it like the force the wave's going to hit you with, right? And anyways, if you square that amplitude, right, because it's amplitude squared, when you double the amplitude, the height of the wave, you square the 2 and you get a 4 here. So you get 4 times the intensity or 4 times the energy when the amplitude is twice the size. And so there's kind of what you can think about. So whenever you see a wave, its amplitude matters, but it matters for energy or matters for intensity. So if you're, say, in at home and you want to listen to music and you buy an amplifier, or if you're in a car and you have an amp in your car, it's to increase the amplitude of the waves by using more energy, right? So adding more energy will increase the size of the wave or the amplitude of the wave, and that's what when the waves have I guess a larger amplitude, they would have more energy and we perceive it as a louder sound. So anyways, why is that? Where did this relationship come from? I'm not going to go into it right now, but I think the best explanation I've heard looks something like this, that work is force times distance, and work equals force is a restoring force. So think negative kx, think Hooke's law. I'm not sure if I talked to you guys about that. I think I did, but force equals kx. So W equals kx squared. Work is change in energy. Change in energy proportional to x squared. All right, and x squared is like the amplitude. All right, so there you go. Small explanation, but it's not super important that you understand that. All right, so in this next part of the video, I want to talk about some applications here of sound and maybe how we perceive it. The first thing I want to talk about, and you can write this down, is the Doppler effect. And this is the change in a perceived pitch, right? How high or low a sound is, or the perceived frequency, when a source moves relative to an observer. So you can think of this being maybe an approaching siren, train whistle, something along those lines. And one thing to remember here is that the source doesn't affect the speed of the wave once it's been emitted. So once the siren or the whistle has left the source, it's no longer influenced by the source, right? The speed of the wave through the air depends on the medium. So how does this work then, right? If the sound is unaffected by the source after it left the source, right? So we're going to do a drawing here, and this one's going to be kind of tough to do. So you might want to hold off on making this drawing and then just explain what the drawing is showing, because it's going to be kind of tough to draw. So what we have is two people here. We have a something making a noise, maybe a police car or an ambulance is driving by, and it's emitting a sound, and the velocity of sound is traveling in this the source is traveling in this direction. The velocity of sound is going to be the speed of sound in air, and it's going to move out in a sphere. But it's going to move. A sphere is going to be created when the source is here. A sphere is going to be created when it's here. A sphere is going to be created here, and so on. And so I'm going to show you those in a second. But why these points are important is because this is the time period, right, from crest to another crest. So this source travels this distance in a period t, right? So that's what we're noting here. Okay, so at each of these points, like I said, a sphere is going to be emitted, because that will be a period, or the time it takes from crest to crest. Okay, so anyways, what's gonna happen then is something like this. And this might look confusing at first, but let's think about what it's saying. It's saying that when the source is right here at position 0, a sphere is emitted, right? And then the source goes to position 1. And so you can see this red dot has this red circle perfectly around it, right? Obviously that's a perfectly drawn circle, not really. But you get the idea, right? That red circle was emitted from that red dot. And if you look, this green circle is centered around the dot at 1, right? And so the sound was emitted there. And then when the source moved further along, and its velocity was to the right, towards Nancy, away from Pablo, it emitted this sphere right here. And then maybe now the source is at position 3. All right, I didn't have a purple dot for there, but I probably should have. All right, so this would be the location of the source right here at position 3. And it's about to emit another sound wave. So what you can see is that because the source is moving forward, the waves still travel outward the same, right? So if you were in the car, right, or the ambulance or the police car, whatever this is, you wouldn't hear any change, right? Because It's just emitting a sound that is perfectly what it should normally do. But if you're Nancy right here, what you notice is that these wave fronts, right, that are separated by a wavelength are no longer separated by the normal wavelength. What would the normal wavelength be? It would be something like this distance right here, and I think would be one wavelength, and this would be two wavelengths, and this would be three wavelengths. But I'm not going to draw that right now. So what she's perceiving are these bunched up wave fronts, right? And since that's a shorter wavelength, that means a higher frequency. Now, why is that true? Because we remember that the speed of sound is not changed, right? It's dependent upon the medium air. But we learned last time that the speed of sound is equal to the frequency times the wavelength. So if your wavelengths, right, this distance from crest to crest, are smaller, if this gets smaller, the frequency gets larger, and a higher frequency is perceived by a higher pitch. So we would expect that Nancy would perceive this siren as having a higher pitch. Now, everything is going to be similar for Pablo, but the opposite, right? That these wave fronts are now separated by a larger distance than the normal wavelength. So we called it wave minus because the frequency is going to be lower. So I'll call this F minus. And in this lower frequency, right, because the wavelengths are longer now from blue to green and green to red, this distance, this is wave minus, that when that wavelength gets longer or greater, right, I'll rewrite that equation one more time. When this gets larger, frequency has to get smaller. And because frequency is lower or smaller, we perceive that as a lower pitch. So this smaller frequency, I guess I probably should use the word smaller there, smaller frequency, and would have been better, but and maybe larger frequency. But you get the idea, all right? So the frequency is smaller, and we're going to perceive this as a lower pitch. So that means that the siren's going to sound, it's going to sound lower as it goes away, and it's going to sound higher as it comes near you. And I actually included a couple videos on Doppler, on the Doppler effect that you can watch right now if you want to pause the video and click on them. They're on Schoology. But I guess I just want to point out a couple things before we move on. And that, remember, there's no change for the source. So once again, if you were in the car or you were riding with the source, you wouldn't notice a change in this frequency or a higher pitch and lower pitch. Furthermore, examples of this, I already pointed out a couple: police siren, train whistle, but this also is perceived with light. So light or radio waves, Doppler radar uses radio waves to locate water particles in the air as they're moving. So moving water particles have a Doppler shift when radio waves are sent out and they hit those moving objects and they come back. Also, distant stars also perceive. You can perceive a well, this wouldn't happen with all moving objects, but objects that are significantly far away, like distant stars, the light that comes from distant stars is redshifted, so toward the longer end of the spectrum, right? Because red light has a longer wavelength than violet light, which has a shorter wavelength, or blue light, right? Because Roy G. Biv. And red has a longer wavelength because it's further to the left. So this is actually evidence that the universe is expanding because this light from distant stars is all redshifted. All right. Okay, so if you want to pause and watch those videos, if you didn't, you can before we move on to the next topic. The next topic is shock waves. And so what this is, and let's go ahead and write this down. if an object moves faster than the medium, than the speed that the waves move through the medium, then the wave fronts overlap, right? And we know that a wave front is where the compression is, but what happens if the object's moving faster and the wave fronts overlap? And we see this all the time, right? You can go swimming in the water and move faster than the waves in the water. A duck will do this, right? A duck moving through the water creates a V shape where crests overlap. So this is actually kind of a pretty normal phenomena that is decently easy to observe. I want to show you a picture on 491. And before I go further, so what we see is something like this. And if an object is traveling faster than the medium it moves through, we can see where these spheres start to overlap, right? Because this object is moving so fast, and you get something like this. And if you are standing, you can see this with the boat, right? As the boat moves faster than the waves are moving through the water, and you get this V shape that comes out, and you see the same thing here. And you might say, well, why does this matter? So what we like to call this is a shock wave, right? And that's so where these crests overlap, and we also experience this with sound. So if an object moves faster than the speed of sound, you notice this with the crack of a whip. That is created from the whip traveling faster than the speed of sound. Just the very end of it, right? So anyways, let's go ahead and put this back up there. Write something down here. So a plane moving faster than 343 meters per second, or 767 miles per hour, is traveling in air at a supersonic speed, above the speed of sound. And when these wave fronts pile up and they eventually reach your ear, if a plane is moving this fast or a jet is moving this fast, it's experienced or heard as a sonic boom. This is kind of like where you see the plane pass you and then you hear the sound, because the plane is out racing the sound, right? It's traveling faster than the sound. And so I have a video of this as well on Schoology, and if you haven't clicked on that one yet, you can click on that and hear and see the sonic boom from a plane. So go ahead and do that now, and you can pause this and come back to this. All right, the last thing I want to talk about is something called beats. And I think I'm going to give you the definition of it, and then I'll try and get my Chromebook or one of the computers I have to play this for you so you can hear it. And what it is a modulation of volume. So it's going to go loud, soft, and you're going to be able to perceive that with your ears due to interference that we talked about last time, where two up waves make a larger up wave, constructive or destructive, where an up and a down wave cancel and cancel that sound. When we notice this when the frequencies are slightly different. I'm sorry if that keeps moving. And this is something that I can show you in the book as well with a picture. So I'm going to go ahead and do that. And so it ends up looking something like this. All right, so what we have here is a red and a yellow wave, if you look at the diagram. And what is going on there, if I can hold this with one hand and point, right here, you see the red and yellow waves are lined up, right? So the up waves are lined up perfectly with the up waves. And you might say, well, what's going on? Why are they lined up and then not lined up? It's because the frequencies of these two waves are slightly different. And when they're slightly different like this, they line up some of the time, and then they line up and destructively interfere also some of the time. So we end up with constructive interference in a larger wave where it's loud and then destructive interference where the red cancels the yellow, and it's quiet. So we hear this loud, quiet as a beat. And not only is this something that we can experience or hear, but we also notice it mainly when the frequencies are very close to one another. Because you might say, well, if this is going on with sound, how come I don't normally hear beats? And so that's a really good point. So I'm going to try and play that on the computer. And then I'll show you the formulas for it. So let me pause it right there so get that going on the computer. All right, so I got my computer going, not my Chromebook, because I think that the speakers on this computer are a little bit better. Actually, I have the Chromebook right next to it, but I'm going to try and do it all on one computer, and because I think it actually illustrates it pretty well. The Chromebook did a decent job as well, but it struggled a little bit more with it. Okay, so I have this tone generator. Let me go ahead and hit play. I have a low frequency right now of 150 hertz. And so we're only supposed to be able to hear down to 20 hertz. I don't know. I don't hear anything. But my hearing's not as good as your guys's, so. Okay, I can start to hear it at about 60, about 50 hertz is probably about as low as I can go and still hear something. I don't have headphones on, I'm just listening to it. I don't know if the phone's picking it up. But obviously it's pretty loud. That's volume though, that has nothing to do with frequency. Frequency is his pitch. And I could go louder, or not louder, sorry, higher frequency. Oh god, but that's very loud. So if I did go up in frequency, I would want to turn this volume down. Okay, it's still super high, but at least now the volume is not as bad, and that's pretty obnoxious. So I'm not gonna go up there and experiment with that right now because I know that I can usually hear on this thing around, when I'm in class, I want to say it's usually around 13,000 hertz, and I can't hear anything above that, but I don't know. Anyways, it's not about my hearing, and usually the students can hear a lot higher frequencies than that, but I don't even like doing it because I don't know, I don't want it damaging anyone's hearing. I don't think the frequencies will, like I said, but you just make sure the volume's turned quite low because I'm sure it could damage your hearing, just like listening to anything for prolonged periods of time could damage your hearing. All right, so coming back to this, I have two tone generators opened up here, and they're both set to 440 hertz, right? This one's playing right now only, so I'm going to turn that off. I'll play it again. I'm going to turn it up so you can hear it. Okay. So I got about 75%. All right. Turn it off, turn it on. I got another generator opened up in this window. I'm going to go ahead and turn this on. All right, got quieter, which is kind of interesting. I think that's part of the problem of using just one speaker here. Not necessarily indicative of the fact that it should be quieter, but all right. So I'll keep the volume about here, 75%. What we're going to do is to experience beats is I'm going to move this from 440 hertz, right? Because they're both playing at 440. I'm going to move it to one of these to 339 or 439, so just down 1 hertz. And you should notice a pattern there. Loud, quiet, loud, quiet, loud, quiet. And in fact, the louds are 1 second apart. Loud, 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 1, 2, 3, 4. So they're 1 second apart, right? 1 beat per second. And wouldn't you know, 440 minus 439 is 1 hertz. So if I kick this down to 438, we should experience 2 beats per second. 3, if I go down to 437, so right now it's what? 1, 2, 1, 2, 1, 2, 1, 2, 1. Should be 3. 1, 2, 3, 1, 2, 3. So musicians actually can use this to tune their instruments because they can detect the beat frequencies when the two sounds are close, or the two frequencies of the two notes, right? All right, let's try that again. So 1 beat per second, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 5, 6, 7, 8, 9, 10. And then I'm just gonna bring this way down. You don't notice it as much. At 220, I did notice something. No, I guess not. So when I'm at 220, and that's at 440, you just get kind of like a tone in the middle, right? So what you're hearing is probably the average tone. So that would be at maybe 320, right? In between the two. Interesting how you're detecting a beat frequency there. At least I can. I don't know if you can. And I wonder if that's something to do with the fact that the 220 is half of 440. Because normally if I just go up to some arbitrary beat frequency like 312, right? And that's what? I don't know, 128 away, right? 128 hertz away. You can't hear anything. You just hear some muddy tone between the two generators, right? Here's 312. Here's 440. We stop 440. That's what 312 sounds like. Right there. Stop 312. Here's what 440 sounds like. So when I play both, it's just somewhere in the middle. You can't detect 128 hertz worth of beats, right? With your ear, at least not easily. You might say, well, I can hear it, but not really. And you couldn't count the number of beats. You couldn't tell me. So only when they're close, right? So if I go to 440, once again, nothing, because they're the same tone. But as soon as I go up, separate them, let's go above 440. 1 hertz, 1 beat per second. 2 beats per second, 2 above 440. 3 beats per second, 3 above 440. You get the idea, 4. All right, so that's pretty neat. And once again, that's a property of sound based on constructive and destructive interference and producing a loud, quiet effect. Okay, so when the beat frequencies, this we have constructive interference when you hear a loud, destructive right here when you hear a soft. And what you should notice here is that how often these crests appear are how often you hear the louds, right? So if the frequency of crests is once per second, so it's loud every second, 1, 2, 3, then obviously the beat frequency would just be 1. And then if it occurs more often than this, then you would have more of these, this brown line, or you'd have more of these crests more often. So a formula that shows all this, there's actually two. The first one just being, what is the average frequency that you hear? So when you have two sounds, right, two frequencies, maybe the 440 and I think it was the 220, then maybe right in between them is the, and you do the math here, you get 330, right? And but the beat frequency is really simple, the formula for it, right? You just take your two frequencies, if this is 440 and 439, subtract them, you get 1 hertz, and the beat frequency would be 1 hertz, so the number of beats per second. If this is 440 and 438, then subtract them, you get 2 hertz. And you can go above as well, so it could have been 440 and 441, you get -1 hertz, but there's an absolute value here, so it would just be 1 hertz or 1 beat per second. That's pretty much it. I just wrote one last thing. It's easiest to detect when the frequency beats is small. And that's about it. So when the tones are similar. Okay, that's the end of the lecture, and we'll move on from here to light. All right, take care. All right, so in the second lecture this week, we're going to start talking about light, light and optics. But here we'll start really generally with light. Next week we'll move on to mirrors and talk about how objects reflect light. So you're gonna go ahead and take notes here. We'll go ahead and say start with just a definition of what light is, and try and get at it from a few different directions. And so light is composed of both a particle, or you can think of it as a particle, but you can also think of it as a wave. So the particle definition being a photon, and the wave definition we're about to talk about right now. Light as a wave is something called an electromagnetic wave, and it's because it's composed of oscillating fields of electricity and magnetism. So we said the field theory is the idea that a particle changes the space around it and creates a field around it, instead of having two objects that create, say, the force of gravity. One object changes the gravitational field around it. And so here we're talking about an object generating a electric field and a magnetic field, right? So light is composed of both of those fields, and these fields are perpendicular to each other. So that's what we're gonna say, but we're also going to call the electric field capital E, the variable. I put a little vector sign over it because it points in a direction, and the magnetic field capital B, also with a vector sign over it. And since these fields are going to be drawn like amplitudes, and they're going to oscillate, say, up and down and into the page and out of the page while the wave moves right or left, we can think of light as a transverse wave. And I think if we see a direction or see a diagram of that, it'll be a little clearer. So here, what I have is light drawn as I just drew an axis here, and we have an up and down field. We'll let that be the electric field, and then a field that goes out of the page and into the page, out of the page and into the page. And you can tell that both of these directions, up and down and out of the page and into the page, are 90 degrees to the velocity. So we can call this a transverse wave. And so what we're going to think of then is light as an electromagnetic wave. We're also going to consider it a type of electromagnetic radiation. So let's go ahead and get a definition for that. And maybe just before we do that, I want to mention what I did last time, and that is that visible light is composed of 6 elementary colors, Roy G. Biv, and I went ahead and labeled them out. But also remembering that the longest wavelength is red, and the shortest wavelength is violet. The lowest frequency is red, and the highest frequency is violet, and the lowest energy is red, and the highest energy is violet. It's weird maybe thinking of colors as having energy, but we have to remember that they're a type of electromagnetic radiation, and so we can consider them to have energy, just a very small amount. So light is a form of electromagnetic radiation. Visible light is a form of electromagnetic radiation that we've talked about, right? But there are other forms. And so I went ahead, and I think I wrote these out last time, and I went ahead and put them on the spectrum. And the electromagnetic spectrum are these, I think it's 7 different forms we have here. And they're listed in a particular order where we have the longest wavelengths, the lowest frequencies, the lowest energies of these forms are on the left. So I know if I was comparing, say, infrared light with microwaves, I would be able to say that microwaves have less energy than infrared light. Would have less energy than infrared light. Or I could say that microwaves have a longer wavelength than infrared light. Or I could say that microwaves have a lower frequency than infrared light. But by that same logic, I could say that infrared light has a shorter wavelength, a higher frequency, and a higher energy than microwaves, right? Because it's on the right. And I didn't go ahead and label those on the right, but I always just label the left side because this is how I remember, right? All the L's, longer, lower, lower, are all on the left. All right. So forms of radiation. All forms don't require a medium. And we mentioned this before. This is how light, how the sun can give off visible light and ultraviolet light that we can't see, and it can travel through outer space and reach us. All forms of radiation, radio waves, microwaves, X-rays, travel at the speed of light. So we should address what that is. We like to represent the speed of light by the variable c, or the constant c. I think the letter c comes from the fact that I think it's Latin. I think it's Ceritas. I can't. Oh boy, it means swift in Latin. Let me look it up really quick. Celeri. I wasn't even close. I was kind of close. And that is Latin for swift. All right. So anyways, because obviously light moves very fast, so that's where they get the letter C from for the constant for the speed of light. It is 3 times 10 to the 8th meters per second, which is, what is that, 300 million? Yeah, 300 million meters per second, or approximately 670.6, so 671 miles per hour, 671 million miles per hour. Whoops. All right, so very fast, right? So just to give you an idea, so I'll write that out too, just so we're clear. So about 670 million miles per hour. So quite quick. All right, forms of radiation. So the way we get these different forms, since all forms of electromagnetic radiation have to travel at the speed of light, is that what we do, if V is constant and it's always equal to 3 times 10 to the 8th meters per second, is we just change the frequency and change the wavelength. So when we have, say, wavelengths that are very long and frequencies that are very short, we have things like radio waves. And if we flip that and we have wavelengths that are very short and frequencies that are very high, then maybe we have something like gamma rays or X-rays, something with a lot more energy. And so all we do is we change these two variables, because they always have to total up to 3 times 10 to the 8th meters per second. We just change those and we get our different forms of electromagnetic radiation, visible light just being one of those forms. So, and I just made a note here of writing what I said before on the a second ago, was that longer wavelengths, lower energy, lower frequency are on the left. All right, so that's about it. Homework this week is going to be a little shorter than the homework last week, and that is going to be to use this template if you so choose, or you can come up with a template on your own, but you're going to go onto Google, look for a picture of the electromagnetic spectrum. So that'll be your title. And I'll go ahead and scan this in, and I will post this on Schoology so you can use this if you like and you don't want to just make up your own. But what you're going to do is give me some units here, a scale of frequencies, a scale of wavelengths, and you should know the units for frequency and for wavelength, and you'll put them there. Here, for a drawing of a wave, and then for magnitude and size, I just want to know what's on the left, right? I think we just said a second ago what should go on the left, right? And for so for this one, for frequency, it should be high or low, and for wavelength, it should be large or small, and the same thing with over here. So you can just tell me that and write that over here, and then you're going to literally draw a wave, right? And you should know something about if the wavelengths are say longer on the left, then the crests should be further apart, right? And then they should be the crests should be shorter, should be closer together where the frequency is high and the wavelengths are low. So I think the wave would look something like this. It would be kind of large and then get really, really frequent right here, and so on. Types of waves, you'll label those 7 types that I mentioned a second ago, starting with radio on the left. And then you'll look at relative size. You know, how big are radio waves, right? And so you can draw a picture of, say, if radio waves are the size of a football field, you can draw a picture of a football field. Uses of the wave, what are radio waves used for? And you just give me an example here and then draw a picture. So here's where I like you to add a little color if you can on your pictures, but I understand if you don't have crayons or colored pencils at home and you can't do that. So you're making your own electromagnetic spectrum here. I always get students that ask me, well, how do we know, like, when I'm looking at the scale, where radio waves stop and microwaves begin? And there's no clear-cut line. So I think, it'll be roughly in a region, but it's a spectrum, right? So there's some blurring together. It's kind of like with the colors, right? It's similar to that, how it changes, but it's not usually on a certain number, right? It has to be radio waves, and it has to be microwaves. There is some, it's just not exact, I guess is the best way to put it. So anyways, that's it for the homework. So it was just to take notes over these lectures and then to create your own electromagnetic spectrum. Next week, I'm going to come back, talk about reflections, talk about mirrors, and probably get into straight mirrors or plane mirrors, and then talk about curved mirrors, concave and convex. So that'll be next week. All right, have a good week.